Bum, bum. There once was a boy named Harry who constantly conquered death. But now that I don't care at all, he is my man. That's actually not bad in terms of delay. Okay, so I'm gonna wait for everyone to get in. My fingers all bandaged because I hurt myself. Hey yo, ha, dum bum ba da dum bum ba dum bum 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 ba da dum bum bum ba da dum bum ba da dum bum ba da dum. This is a long topic today. I don't like long topics. I feel tedious to cover in one sitting. Especially because, like, this is the type of video I could make 3 or 4 different small videos on. But this is one long straight go, and it's live. If I had it my way, I would be, well, if I had it my way and I had my right hand, I would be drawing diagrams and stuff, and then do a separate video on coding it. But, well, first, I don't have my right index finger, and my right hand is my predominant. Yusef, what's the best way to practice for the upcoming test? Do the practice test. Do the practice test, code a bunch, and do the assignments. If you do the assignments and you finish the assignments, do them again. Start from scratch and do not use the same method. I guarantee you that's like the best way to study, in my opinion. If you can go into an assignment and you have the one rule of I'm not allowed to use my previous solution, you will definitely get a better grasp on how you code, because I'm telling you, there is more than one way to code anything. Regardless of what you code, there's always more than one way. But yeah, the tests are, you see it and you either excel or sink. Another good way to study for the tests, I've heard this one's common, you just watch a whole bunch of coding YouTube videos. I did this one. I watch Coding Train religiously. I love his live streams, I love his videos, and they're fun because he talks about everything. He talks about every step, his entire train of thought, Wikipedia articles he uses to reference code and stuff like that. It's great. Coding Train's great, but he does JavaScript, not Python. That might turn some of you off. It might intrigue some of you. I don't know. 2 minutes. 2 minutes. Ladies and gentlemen, 2 minutes. I don't know if the chat box is working. I didn't check that on the live stream. I'm gonna assume it's working. When I see another message come in on the chat, I will look at the live stream to see if the message pops up on the live stream as well, because if it doesn't, then I'm just going to turn it off. It's a waste of my screen space. I'll fix it for the next one. Yeah, just waiting another minute. This is a long tutorial. Very long, very in-depth. I'm not going to have a lot of time to pause, but I will attempt as much as possible. Good morning. Okay, I see a Serening good morning appear on my live stream. So I think the chat is properly hooked up. Also, good morning, Sarah. Today is a big topic. Get tucked in, guys. This is gonna be fun. Also horrible. I have a lot to cover. I've got to get you guys to learn MergeSort. I'm going to teach you guys how to generate a Pascal's triangle. Binomial Expansion is what it's technically called. We're going to talk about the basics of recursion using Factorial, GCD, greatest common denominator problem, and your simple recursive. These two are our big boys, and I'm saying MergeSort is the ultimate boy. He is le boy grande. But out of curiosity, before I begin, can I ask those who are here, have you seen or heard of the concept of recursion already in lectures? I want to know how screwed I am. Like, am I starting from literally nothing? Or can I just assume that you guys should have seen it already and move forward? Because I would prefer to know whether or not I need to spend 8 minutes doing these first two examples. We looked over Factorial and Fibonacci. Okay, I'm not going to do Factorial then. Factorial is the easiest one. If you guys want to see Factorial, I can just code it real quick. However, I'm defining Factorial because we will need it for Pascal's triangle, at least how I'm going to be doing it. It won't be how other people do it, but Fibonacci is, Factorial is if n is 0 or 1, return 1, else return n times factorial n minus 1. That's all Factorial is. Basically, you are going to be creating a whole bunch of calls to the same function, and it's going to generate one long string of values, and you're just simply going to combine the long string into one. Please tell me my live stream is not dead. Because right now I'm not seeing anything. Oh no. My camera died, didn't it? Haha. Yeah, my camera died. Hold on, I can fix that. Ah! Oh, he looks so stupid. My webcam is dead. That's fine. That's fine. Who cares about my face? I don't need a face. GCD. GCD is another one that's actually really easy. What it's going to do is if b equals 0, we're going to return a. Or what we're going to do is we're going to return the GCD of a mod b, or sorry, b a mod b. This one's a little more complicated to explain and understand because a mod b, in my first example, 12 mod 48 is 0, so then b becomes 0, and a becomes 0, but no, a becomes 12, does it not? 12 or 48? I can't actually remember how this one. I think I might have this backwards. It might be b mod a, not a mod b. No, it is a mod b. I'm gonna have to look into how this works. Just one second. If I do 12 mod 48, does it return 12? Okay, it does return 12. So 12 mod 48 returns 12. So then that becomes 12, and that becomes 48. So this first test case becomes this second test case. Fun fact, if you ever don't know why something's working, just do it by hand. But these are the easy ones. No one cares about... great. I'm having a bit of difficulties right now, guys. My peripherals do not want to play nice with my laptop for some reason. So I'm going to kill my webcam, actually. And I'm going to pretend I don't have it at the moment. Oh, my entire computer's acting up now. I apologize. The universe isn't content with how everything is. Please give me my mouse back. Well, just give me a second, guys. I'll eventually get control over my laptop again. because it's not having a good time. We're going to turn off that, and we're going to turn off that. I will fix that for the next live stream, but right now it's pissing me off. So those are the easy guys. You can Google those if you don't understand them. However, what I have to do in this tutorial is teach you guys the really hard ones. Mainly, how to sort using recursion. Because sorting is actually, like, in terms of recursion sorts, there are a lot of really important recursive sorts. The famous ones are quicksort and MergeSort. However, you can write a recursive sort for, like, if you want to use binary search and sort it into a tree, that could be recursive. But yeah, so we're going to take a look at something really simple. Pop out the minimum element and put it in front of a new list. So in order to do recursion, we have to identify two things. We have to identify a base case and a recursion case. The base case is going to be, what do I do if there's nothing left? So what is my base case in this case? Well, there are two. If L is an empty list, then what would I return? Well, I'd just return an empty list. Well, what's my second base case? If the length of L is exactly one element, well, I can return L, can I not? Because there's nothing left to sort. I only have one item. So these are my two base cases. I can combine these into one if I wanted with an OR statement. That's pretty. And then there's the recursion step. Oh boy, the recursion step. This is a big one because we're going to have to do two things. We're going to have to remove the min element, which is easy. We can just do m.add. M equals the minimum element, and now one thing I never remember, and I don't know if you guys can tell me, is dot remove for lists like L equals L dot remove? Or is it just a direct mutator and it's just L dot remove? I think it's L dot remove. Either way. So what we're going to do is we're going to remove M now. So we found the minimum element. Yeah, it's just L dot remove. Thank you, Haley. So we found the minimum element. We're going to remove it from the existing list. And what we're going to do is we're going to return a list of that minimum element plus. Now, would we just do this? What's wrong? Did anyone see why this won't work? A list of just the minimum element plus the rest of L. I want to see if someone can call me out. You'll have a duplicate element. I'm pretty sure remove just removes the first case of the occurring element, but that's not the problem. That's not the problem. What is this case? It's the recursion case. What am I not doing? If we look at both Factorial, if we look at Factorial and we look at GCD, what do the recursion cases do? Yeah, I'm not using the function. It's recursion. I've got to call the function again. Boop. Bada bing, bada boom. So I've generated some basic test cases. What it's going to do, makes a random list of n elements and tests it. So what I'm going to do is I'm going to show you guys some tests. Let me pull this guy down a bit. Why is that not working? Huh. Do I not have... I just click the testing button. There we go. There we go. So now I have some random list, but I've sorted it. List after sorting. Okay, so that's helpful. Let's see if it works with a list of 20 items. Okay, so someone's like, why? Can you explain why you have to call the function instead of just returning L? Well, I can show you. L is completely unsorted. If I have a list of 5 items, what this did is it found 0, it popped 0, put it at the front. I did not save. So this was completely unsorted. It found 0 and put it at the front of the list, but it didn't sort the rest of the list. What is makeList? It is a function right here, makes a list of random numbers from 1 to 100. I created these 2 functions just to make this tutorial a bit prettier. So the reason I have to keep sorting the list is because although I sorted the first element of the list, I have to then sort the second, and the third, and the fourth, and the fifth, and the sixth, and the seventh, and the eighth. You see the difference? Because if you see, 97 is not bigger than 73, but here there's no number out of order. So I want to take a look at this more in depth, however, because I don't think that this is really helpful. I'm going to print L every time that this function recurses. And I'm going to simply use this guy here that doesn't have my printing function that I made. So if we take a look at every step of this function, it starts with the entire list, and one by one, the list is shrinking by exactly 1 element. What happens to these elements? They're getting thrown inside this return statement. So L is progressively shrinking. However, the output of my function, because they all pool into one big return, the output is getting progressively bigger. So if I print this and run it again, you can see my list gets shorter because this end list is one by one getting the new elements. I thought that would be cool for you guys to see. If you want to see how is the list getting sorted, though, here, the recursion case takes the minimum valued element from the list every time. So you can see here, I have 0 in this list, and then there's no 0 here. And then the smallest element in this list would be this 29, but there's no 29 here. It keeps finding the smallest number from the original list L and throws it into a new list. Then it recurses off of the remaining items and keeps throwing it into this list of M. Item by item, we take from L, throw into M. That's one of the best ways to understand it. So if you were to find the minimum element from every list, you could see that as it gets popped, that's the order of the items in this child list. All right. Think I've covered that enough? Let's go on to the hard guy. Yeah, binomial expansion is actually extremely hard, but the concept is easy. Pascal's triangle is the following concept. You have a list of numbers, and the next list is the sum of 2 side-by-side items. with the only exception being this case here, because he's 1, 1. So what you would do is for every list, you push the number 1, and then you add the next number with the previous number. So 1 plus 2 gets you 3, that's why 3 is here. 1 plus 3 is 4, that's why 4 is here. 3 plus 3 is 6, that's why 6 is here. 3 plus 1, that's why 4 is here. It's a weird concept, but I'm not here to explain Pascal's triangle, I'm here to show you how to code it. And it's not easy, I'm telling you that right now. So, I'm going to need a base case. We always start with a base case. Base case. And what is my base case? Well, my base case is if n equals 1. There's no Pascal's tree of 0 height. You will always have at least one element in Pascal's tree. So our base case is going to be 1. Now, what I'm going to do is I'm going to skip the whole return garbage. I'm going to print the tree with every step. So that way I don't have to print it here. So what I'm going to do is I'm going to print a list containing only 1, because that's our base case. And additionally, I'm going to return it as well. So now I've covered this guy here. I now need to cover all these guys. Ha! Oh, here's where it's... Welcome to hell, ladies and gentlemen. Else. Da 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 da. I'm gonna need to see... Let's take that from the top. All right, ladies and gentlemen, I'm gonna need some help. For example, in order to generate this line, I need the previous line. So what I need to do is previous equals, and I'm going to call binomial. It's not called binomial expansion, it's called Pascal's triangle. That's what I named the function, since that's what I thought all of you would know it as. It's going to call Pascal's triangle of n minus 1. What I'm going to do is I'm going to immediately recurse. Before I do any printing, I'm going to start from the bottom, and I'm going to work my way up the tree all the way to the base case before anything happens. Is this memoization? No. Memoization is the act of taking this previous case and storing it in memory permanently. So that way I never have to call the function after it's been called once. So the problem with the way I'm doing it now is if I were to run the function twice in a row, I do have to call prev again. But if I already had if I already had Pascal's triangle 4 saved in memory somewhere, I would, instead of calling it, I would just use the value there. I hope that helps kind of clarify. So, I'm going to use a while loop, because I find while loops extremely helpful. That being said, if you guys want me not to use a while loop, call it out now. The prev is just calling back the function, right? Yeah. So basically, I'm starting here. This is basically where I've started. However, I can't do anything without this guy. And 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 this is the only guy that I can actually calculate. So what I've done is I've asked prev to basically go to the beginning and work my way back towards the top. All right. Haley would prefer I do for loops. Okay. Yeah. For loop is much better. So for I in range. And what I'm going to do is I'm going to go to the n minus 2 index. So one thing you can see, this is n1, 2, 3, 4, 5, 6. Notice how the length of the list is always n items. This allows me to skip having any of these length shenanigans or anything like that. I'm simply going to go 1, 2, 3, 4, stop. The reason I'm not going to do these two, I'll show you guys as I am doing it, because it's a little harder to explain. However, I am going to still need a local variable outside, and I'm just going to set it to called J for now. You'll see why I'm doing that. The reason that this is for a while loop is actually because the counter variable is used after the loop. So, yeah. Next, I need some start, right? Because if you think about it, if I have this guy, there is no 1, 1. I can't do that because there's nothing before it. There's nothing after it. I need a list to start. Why n minus 2 again? You'll see. You'll see. So if this is 3, I already have done 0. I have to do 1 plus 1 to get 2, and the last element is always 1. It's hard to explain. I'm not gonna lie. However, I need some sort of line item. I do have to keep going. I can't really stop to explain every decision just because this guy, if I do not teach you this, you guys will fail your midterm. Like, if I do not teach you this guy here, you will not be armed with the knowledge to take your next test, so I need to keep going. I cannot stop. Anyways, so I'm going to have a line, and since I know that the line always begins with the previous line before it, so if I think about it, it always begins with the first element of the previous line, which is 1. So I can either type 1, or you could type prev 0. It's weird. I'm going to keep it as prev 0 because that's what Nick wants us to teach it as, but you could literally just type that as the number 1, because the first value is always the number 1. I don't get why he wants us to do it this way. But anyways, so what I have to do is I have to, with every loop of this for loop, append a new value to my list. And what is it going to be? Well, it's going to be prev at I plus prev at I plus 1. It's the previous value, so 1 plus 5 gets me 6. I can now append 6 to my list. 5 plus 10 gets me 15. I can append 15 to my list. 10 plus 10 gets me 20. I can append 20 to my list. Notice, though, there's no point in me doing 10 plus 5 because I can just copy the list and reverse it. Does that make sense? I can take these existing elements and just be like, cool, I'm done. I think that's how he wants us to do it in this example. Oh, and that's why it's n minus 2. Yeah. So there's no point in me covering these guys because they're already. There's no point in me covering the last n elements because they're already there. It's weird. This algorithm is actually like really cool from a theoretical concept, but could you repeat that? Look at this. I have 1, I have 2, I have 1. If I have... Actually, it's better to look at 1 and 3. I do 1 plus 2, I get 3. However, do I have to do 2 plus 1? I know that eventually I'm going to get to a center item, and then the remaining items were already in the list. Also, I'm going to keep setting j to be equal to I because I want to know the index I start, or I stop at, because that's where I have to put it back, right? Because I have to append the elements I just ignored, because I'm not doing these two, because I'm doing these guys. It's weird. Actually, I think I have this wrong. Range n minus 2, because this is n, I have no element here, and I'm not appending 1, so I'm appending that. Oh no, I am actually straight up adding the 10 and 15. I'm sorry, guys. Nick is really vague in the procedures he wants us to take, because he actually gave me a text file like, I want you to do it this way, and talk about why I want you to do it this way. And I'm like, Nick, because I'm going to tell you right now, this is actually the worst way to do a Pascal's triangle. So I'm going to basically re-explain this entire algorithm, guys, because, well, Nick. Why is it n minus 2? Well, if my n is 6, the previous list only has 5 elements, which means that there is no element 6, and there is no element 5, hence why we're doing n minus 2. If you have time, could you show us your way after? Hell yes. In fact, I'm actually going to say, I'm going to show you the example. I'm going to show you the better way to code a Pascal's triangle. Yes, Matthew, you are correct. N choose R is the only correct way to do this. Whoops, it's not I, it's J. Wouldn't it make more sense to do I in range of len prev minus 1? Not quite. So, and if you look at Pascal's triangle, because I start by appending a 1 to the list, I then need to calculate 2. What is 2? It's 1 plus 1. If I want to get this 3 here, well, it is 2 plus 1. If I want to get this 6, it's 3 plus 1. And I'm appending it to the list. So it wouldn't actually work if I did prev minus 1, because I would be getting this element, not this element. I'm already starting with a 1 in my list, so I'm actually 1 item forward, if that makes sense. This is a horrible way to do it. I did mention this to Nick. You guys want to see the better way? Because I have time before I have to cover MergeSort. I'm going to redo it here. I'm going to need a function called choose. Choose is a really, really good function because, fun fact, a Pascal's triangle is literally every value is n choose r. So what is the formula for n choose r? It's factorial n divided by, whoops, I have to return this. It is factorial n divided by, and I'm not actually, let me Google the formula for choose. And choose R formula. And choose R. No. show me the R factorial times n minus R factorial. There we go. I hate Google. M factorial divided by m minus R factorial times, yeah, thank you. Son of a... Okay, Google, shut up. I'm fighting all of the technology in my house, everybody. I apologize. All right, Pascal's triangle using n choose R. So how do I want to do this? Well, do I even want to use recursion is the question, because this is a lesson about recursion, right? So I should teach you guys recursion. So the base case is going to be the same. If L, why am I caps locked? If len L, or whoops, there is no L. If n equals 1, return 1, not 10. Oh, apologies, I have an itch. Ah, my computer's frozen now. How many of you guys hate me? There we go. Yeah, this is not worth recursing. It's just for I in range n. for j in range of n minus I plus 1, I'm going to simply print, I'm going to print a space. So if you guys didn't know, you can actually change what print does by force. It's actually pretty cool. Then for j in range I plus 1. I'm going to actually make this a triangle, by the way, guys. That's why I'm doing the first print statement. So I'm going to use my n choose r formula, and all I'm going to do is print choose I j. I kid you not. So what I'm doing is I'm preventing it from printing a new line. So print by default is the following: end equals \n. However, you can actually override end to be whatever you like, which is why I'm doing this. So if I just print this without any recursion, if I print Pascal's triangle 5, well, I actually get a triangle. It is cool. Recursive NCR, yeah, recursive NCR is great. It's not more effective than this version, but it is almost more effective. I just wanted to print integers because those points are messing off my triangle. Look how pretty that second one is! Yeah, yeah, Haley, you are right. Recursive choose is on the assignment, which is why I can't show you the other method. But yeah, this is small and it doesn't use recursion. Because fun fact, guys, recursion encoding, except for Haskell for the most part, recursion encoding sucks. It is actually like slower most of the time. However, you guys will have recursion. I know, Ella, it's so pretty. Yeah, but this is what Nick wanted us to teach you. Literally, put a 1, then do 1 plus 5, put a 6, 5 plus 10, put a 15, 10 plus 10, put a 20, 10 plus 5, put a 15, 5 plus 1, put a 6, and then throw a 1. That's why recursion sucks. Yeah, recursion is horrible, and this method is horrible. Because the way I would have done it is I would have just gone to halfway through the list and then simply mirrored the reverse list. Thinking is overrated. Because yeah, if I go to m minus 1 over 2, and then j dot append line -1, I believe this does the same thing. And this was the way I wanted to do it. Unsupported operand type for list. Sorry? Oh, it's not dot append. It's plus equals. Because I don't want a list inside a list. I want... Yeah! Yeah, this is the way I would have done it. I don't want a list inside a list. What I want to do is I want to simply generate these items and then reverse that list and combine them. I don't see why Nick wants you to go through every element. Like, I get that it's more reliable his way, but this is just where my brain wants to go. And there's no need for this stupid J, which means that there's no need for while loops. CompSci makes me realize how smooth my brain is. Yeah, I chose this as my permanent field. Now, this method's not perfect. You see how there's 2 and 6 duplicated. So basically, you need to actually detect if the previous... If we get this question, we could do it this way. If the question wants you to do it recursively, then you have to do it recursively. However, yeah, you could. The only thing is you have to code in an if statement that finds if n is a odd number, it recurses. So I have to add in if n mod 2 equals 1. Like that, however. I think that fixes my error, because you can see there are double 2s. Crap, that doesn't fix the error. Huh, Nick might actually be correct. We might not be able to do it my way. Who knows? Either way, I have to teach you guys MergeSort. I cannot avoid teaching you guys MergeSort anymore. Yeah, I don't like Nick's way. However, I have to teach it Nick's way. MergeSort. Basically, as long as the code works, we don't care how you choose to do it. We really don't. MergeSort. I think I found a video actually for you guys that explains it better than my diagram does. So I'm going to show you guys this video. I don't want to get copyrights, but oh well. Ah, that is loud. All right. So as you can see, what it's doing is it takes an array and divides it in half. And it's going to keep dividing in half until it gets a whole bunch of single items. Now, what it can do is it merges the items into their respective list. So you can see how it's comparing elements one at a time and throwing them in a new list. And I like this video. I think this is actually like pretty genuinely helpful. So now the left list gets appended, then the left list again, then the left list again, and then the right list. So the fun of this question is all in merge. The entirety of this question is merge. So I've coded a merge function, and I've coded a MergeSort function. And this is going to be both fun and also not at all fun, because MergeSort is pretty complicated to code. So what is my base case for this? So if L is a list, what is the base case? Well, I'm pretty sure it's obvious. If the length of L is less than or equal to 1, so if my list is 1 or none elements, I'm just going to simply return L. It's the same base case we used in our simple sort. So if length of the list is 1 element or less, we're simply going to return L. Now the else case. Well, what does he do? I'd close the video. Well, he divides the list in half. So we know that we're going to need the length of the list. And what we have to do is we need to generate 2 sublists. Now, I don't know why I created this variable, because I can just call length over and over. So sublist 1 is going to be a list, and sublist, whoops, I can't type with my index finger because I was injured, so is going to be a list. But what are these sublists? Well, as you can see in my example, I have a sublist 4710 and 253. It's literally just me placing a little line right there. That's all I do. I simply divide the lists in half. So that's what I'm going to do. I'm going to start from, I'm going to copy L, I'm going to start from 0, and I'm going to go to the length of my list divided by 2. So what's my second sublist? Well, it starts at the length of my list divided by 2, and it takes the rest of my list. This is so easy to do without recursion. Yeah, it is. It really is. But it is preferred to do it recursion. So this will take the entirety of my list up to this point, and this will take the rest of the list. And now I have 2 sublists. So I'm going to print both of my sublists. Sublist. And the way I'm going to do it is I'm going to use an f string, so that way I can throw in a new line character like this. And I'm going to take sublist 1. Why the double? Well, is there an index 3.5 in a list? Double index is the exact same, so // is exactly equivalent to math.floor a/b. If you guys didn't know, these are strictly equivalent statements. The left side and the right side are the exact same. It's actually really helpful when you're working with lists to always use //. So I'm going to print my 2 lists, and then I need to return. Well, what do I return? And I just realized I have a return right here. Well, let's imagine I've got to this step. What do I need to do? Well, I need to break these 2 guys into more lists. However, I also know I'm going to merge them again. So I'm going to call merge. However, I'm going to call it on MergeSort sublist 1. Oops. And MergeSort sublist 2. So what this is going to do is it's going to recurse down to this, and then merge is going to put them back together like this eventually. This is why it's so tricky to do MergeSort, is because you're calling the recursion inside of a parent function. And this is totally allowed. It will take it step by step because each of these are merged lists. So what is merge? Ooh. Merge is complicated. So I'm going to actually create a answer list. I'm about to show you what merge does, Matthew, and I'm sorry, it's a pain. So what I need to do is I need to go through list X and list Y. And while one is full, I need to keep appending. So the way I'm going to do that is while the length of X plus the length of Y is greater than 0. So my my stopping point for this loop is when both lists are empty. So if one list has a length, this condition won't be true. Next, we're going to do something disgusting. We're going to actually, by hand, manually, code an if statement for every case. And there are 4 cases. So, if the length of X is equal to 0, so therefore there is no Y, all I'm going to do is I'm going to say ands plus equals Y. I'm going to take the list of Y and I'm just going to throw it in the answer. X is empty, the Y is already sorted, so therefore we're just going to throw Y on the end. Additionally, we have the same case for the length of Y. If there's nothing in Y, we're going to throw X into the answer. elif. Yeah, I told you there are 4 cases. If the element at x0 is less than the element at y0, then what we're going to do is we're going to have ands plus equals. And actually, I'm not going to use plus equals. I'm going to use dot append here. So that way I don't have to put weird brackets and stuff. So I'm going to append x0 because it is the smaller item. I'm then going to say that x is equivalent to x, but without that first item. I'm going to pop the first item out of x. And then it's going to loop again. So what do you guys want to think this guy does? Wait, is merge a built-in function? No, I'm coding that right now. I'm coding that literally before your eyes. So what then does this guy do? If this guy appends the head of x because it's smaller, well, this guy would append the head of y because it's smaller. Huh. That's pretty cool. And if you think about it, this is all 4 cases. The only caveat, I didn't know if you were just explaining or going to be... No. I'm explaining it, but I'm using it. We're using this baby right here to do this baby right here. So what MergeSort does is it breaks it into a list of all these items. Okay? Merge then says, okay, I'm looking at the list 4 and the list 7. I did it the wrong way here, but I can fix that. So 4 is going to be my list X, and 7 is going to be my list Y. Is 4 empty? No. Well, is 7 empty? No. Neither of these lists are empty. Is 4 greater than 7? Yes. I can now throw 4 into my new list. Then X is empty. So now I can just take Y and I'm going to throw it in. So I would get 4, 7. I wouldn't get it like this. Fun fact, if you take an algorithms course, they teach you to do it the way I typed it before, which is why I did it that way. We then do the same thing over here. We're going to say 10 and 2 is going to be my lists. Or actually, we're not going to do it that way. We're going to do it this way. 2 and 5 and 3 are going to be my lists. I know it's confusing, but it's easier if I do it this way because you get to see it step by step. So 2 is X, 5 is Y. And it's like, cool. Is X empty? No. Is Y empty? No. Is 2 smaller than 5? Yes. Throw 2 in the list. So this list is just 2. Next, this guy becomes empty. And is X empty? Well, yes. Cool. I can just take 5 and throw it in this child. Okay? Now I have this case. We'll let 4, 7 be X and 10 be Y. Is X empty? No. Is Y empty? No. Is the head of X smaller than the head of Y? Yes. Throw it in. Then we remove 4 from that list. Do it again. Is X empty? No. Is Y empty? No. Is the head of X smaller than the head of Y? Yes. Throw 7 in the list. Remove it from that guy. Do it again. Is X empty? Yes. Cool. Take 10, throw it in. We're done. Does that kind of make more sense? This guy is the ultimate, case analysis. So, you know what? I'm going to do this guy by hand. We're going to do this entire last line by hand because it's going to be the ultimate explanation. Let's go. Let X be this guy, 4, 7, 10. Let y be this guy, 2, 3, 5. Is x empty? No. Is y empty? No. Is 4 smaller than 2? No. Is 2 smaller than 4? Yes. Conditions. Is x empty? Y empty? X smaller than y? X greater than y. Those are your four conditions. I gotta hurry this up because I gotta get to my office hours, guys. We're out of time. Anyways, you take 2 because he is the bastard child, and you throw him in. Next, is x empty? No. Is y empty? No. Is 4 smaller than 3? No. Is 3 smaller than 4? Yes. Throw 3 in the list. Take him out of this list. Okay. Is x empty? No. Is y empty? No. Is 4 smaller than 5? Yes. Take 4 out of this list. Put him in this list. Is x empty? No. Is y empty? No. Is 7 smaller than 5? No. Is 5 smaller than 7? Yes. Woo! And now, is x empty? No. But is y empty? Yes. And notice how x is in order. So all I have to do is, without even hesitating, I can take 7 and I can take 10 and I can just throw them in and delete it. We're done. That's what MergeSort does. Every time. It sounds exhausting. However, notice how we've sorted 6 elements in 1, 2, 3, 4, 5, 6, 7 steps without having to... What if x was not in order? Well, that's the problem. X will always be in order. Because MergeSort breaks the lists down into literally one item. This is where merge starts happening, Arya. Which means that because merge will happen like this, it looks at 4 and 7 and puts 4 and 7 in order. It looks at, say, 2 and 10 and puts 2 and 10 in order. It looks at 5 and 3 and puts 5 and 3 in order. Or you could think of it like this. It looks at 4 and 7, skips over 10, looks at 2 and 5, and skips over 3, then combines them into one big array. No matter how you choose to do it, as long as the merge step is looking at individual items, it will always be in order. Like, I could literally make it so instead of 10 waiting for the next turn, I could take 10 and 2, make them a sublist, and they would be put in order. Then I could take 5 and 3, make them a sublist, and then all I would be doing is saying 5 and 3 gets to wait, while 4, 7, 2, 10 get to merge. Then 5 and 3 gets to merge with the final list. No matter how you choose to break up the lists, as long as you get to this middle case, no matter how you choose to merge, if you're merging 2 lists at a time, it will work. That's so complex for 6 numbers. Yes, but imagine how complex this would be for 10,000 numbers, and how long it would take to do MergeSort, which does so many bulk things at once, as opposed to simple sort, which finds the n, like finds the m value, takes that m out, and puts that m in a new list. So if your list in this case were the following list, so let's say I had the list of 10, 9, 8, 7, 6, 5. This is actually worse, because what I have to do in order to sort this is I have to go, is 10 the smallest? No. Is 9 the smallest? No. Is 8 the smallest? No. Is 7 the smallest? No. Is 6 the smallest? No. Is 5 the smallest? Yes. Delete 5. Put 5 at the beginning. Then I have to go, is 10 the smallest? No. Is 9 the smallest? No. Is 8 the smallest? No. Is 7 the smallest? No. Is 6 the smallest? Yes. Take 6, put it after 5. Is 10 the smallest? No. Is 9 the smallest? No. Is 8 the smallest? No. Is 7 the smallest? Yes. You see how ineffective this is? This always runs a ridiculous amount of times in a bad list. MergeSort is actually really effective because it's not scanning this list. it doesn't care what numbers these are because it just breaks it down to a whole bunch of numbers. These instructions here, they take no thinking whatsoever. This is where all the thinking happens. So if you want to think about it, MergeSort only actually uses 4 steps to sort these 6 items, where if you had the 6 items in simple sort, you would run 6, then 5, then 4, then 3, then 2, then 1, which is insane. That is 6 times 7 divided by 2, so 42. That's 21 steps. So simple recursive sort takes 21 steps. MergeSort, it's 6 steps times however many comparisons you have to do, which definitely is way smaller. I'm promising you, for really big lists, MergeSort is so much better than most sorts that you can think of. MergeSort is what we comp sci like to call a O of n log n algorithm, meaning that on average, or like, actually, this is for the worst case. For the worst case you can think of, it will run n times log base 2 n times. So for 10,000 elements, this runs 10,000 times log base 2 10,000, which is barely greater than 10,000. If you were to do the same thing for the simple sort that we have here, this guy is O of n squared time, which means that on your worst case, he runs close to n squared times, meaning that he could run 100,000 times or 1,000,000 times for what this could do in, let's say, 10,000. MergeSort is much better than simple sort. However, there are sorts better than MergeSort. For example, MergeSort is commonly referred to as less than quicksort because the worst case in quicksort almost never happens, and both of these are really bad to time sort. And all of these fail against Python's list.sort because, fun fact, Python cheats and sorts your arrays for you. Yeah. Anyways, that's a fun fact at some really complex stuff, but MergeSort is actually really good. Anyways, I have to get to office hours. If you guys have questions, come on by. I'm going to be there forever. And by forever, I mean for the next hour. So, yeah. Bye, guys. And remember, we all hate Pascal's triangle. Every single one of us hates it. If you were to lose... Yes, we had last year in the test, we had people sort... we had people code a brand new sort very similar to MergeSort. And I believe that this question will happen for you guys as well. We tell you exactly how to code it, and if you do not code it exactly that way, you fail. You fail the question, you get a 0. The best thing about recursion is we can count how many times the function is called, meaning we know exactly the number of times the function should be called if you code it correctly. So if we ask you to use a recursion question on a test and you don't do it recursively, I guarantee you will fail. That is a promise. Because I code those questions by hand, and I find out the exact number of recursions it should take, and I compare against... Now, to be fair, there are many different ways to code MergeSort. For example, you could actually have it one by one merge the head of y instead of just taking all of y and adding it. However, that increases how many times you call merge, which means that increases how many recursions you get. We account for this. We give you a kind of an epsilon range of plus or minus. Anyways, I've got to go, guys. I will see you in office hours if you want to continue this discussion, or you can use Piazza or email me or ask me to call you on Teams because I do that too. Bye, guys.